Hello, this is Joshua Cooper, and today I will be explaining the basics of how batteries work, and explaining a battery design that me and my teammates in the lab created and tested. This video is intended for an audience who has at least taken a high school chemistry course. As you probably know, batteries are used as a way to store energy so they can be used later. In general, batteries store this energy by processes called reduction and oxidation chemical reactions. When something is reduced, it gains an electron or electrons. When something is oxidized, it loses an electron or electrons. Reduction and oxidation reactions happen in pairs. When one chemical species is oxidized and loses an electron, it transfers that electron to the species that is reduced and gains an electron. The reason that these reactions lead to the release of stored energy is because certain chemical species are more stable than others. In other words, it is more energetically favorable for electrons to belong to one chemical species than another. The metric for which species are more favorable to accept or give away electrons is called the reduction potential, which is measured in volts. It is energetically favorable for a species with a higher reduction potential to gain electrons from a species with a lower reduction potential. The higher the difference between these potentials, the more energy can be released and used. So now that we understand where the energy in batteries comes from, let's talk about the basic parts of a battery. The three main components are the anode, cathode, and electrolyte. When using a battery to power something, the anode oxidizes a species in your system. On the other side, a cathode reduces a species. The electrolyte is made of ions in solution and is responsible for allowing charge and chemical species to be supplied to the anode and cathode. The reduction potential for the anode and the electrolyte is higher than the reduction potential for the cathode and the electrolyte. The difference between these two reduction potentials determines the voltage of your battery. When you go to the store and purchase a 6-volt battery, now you know where that number comes from. It's a measure of how much more favorable it is for the anode to take electrons from the species in electrolyte than for the cathode to take electrons from the species in electrolyte. Now let's talk about how the stored energy in a battery is used to supply power to a device. When your anode and cathode sit in the electrolyte, the anode starts to build up a negative charge as it takes in electrons, which are negative, from the solution. The cathode starts to build up positive charge as it gives away those negative electrons to the solution. When you use a wire to connect your anode to the device you want to power and the cathode, the electrons that have built up in the anode repel each other because of their like negative charges. They are attracted to the positively charged electron-deficient cathode. This causes a current to flow between the anode and cathode. Current is the electrical charge flowing per second measured in amperes. By convention, current is in the direction of the movement of positive charge. In this case, our charge is being carried by the electrons. To get from the anode to the cathode, they must go through the wire and connect a device where they can be used to do something useful, such as turn a motor, produce heat, or produce light. The electrons transferred through the wire from anode to cathode allow the cathode to continue to reduce species in the electrolyte, and the anode continues to oxidize species in the electrolyte. The battery will run out of energy and stop functioning once any of the reactants for the reduction or oxidation reactions happening at either the anode or cathode runs out. This could mean you have run out of chemical species in your electrolyte, or you have consumed all of the material in your anode or cathode. For our battery design, we wanted to focus on increasing our power output even at the cost of battery life. In the case of a battery, we can think of power as how much energy the battery is outputting over time. The higher power usage of a battery, the quicker it will run out of energy. In other words, increasing the power output of a battery will decrease that same battery's operating life. The SI unit for power is watts, or joules per second. To calculate the power of a battery, we measure the voltage of the battery and the electrical current produced by the battery. By multiplying these quantities, we get the power of the battery. Therefore, as you increase either your voltage or your current, you are increasing the power of your battery. Creating and testing powerful batteries is very relevant economically and environmentally in today's society. When we produce energy from green and renewable sources, such as solar and wind, we have to store that energy for our later use. One way to store that energy is in batteries. One challenge that needs to be addressed if we are to reduce our reliance on fossil fuels is making batteries powerful enough to replicate the large power output of combustion engines and generators. For example, there is a growing market for battery-powered cars, with global electric vehicle and hybrid vehicle sales surpassing the 1 million mark in 2017. Moving a 2,000-pound car upwards of 80 miles per hour, even in good weather conditions, requires a lot of power. Design challenges like these are what drives the study of high-power batteries. Over the course of 2 lab sessions, my team tested different ideas to try and optimize the power of our battery using the resources available to us. As the container for our battery, we had a 12-compartment cell. First decision we had to make was which metal wires, out of our available options, to use as our cathode and anode. With some research, we found that aluminum and copper had the largest difference in their reduction potentials, which would lead to the highest voltage. Initially, we chose potassium chloride as our electrolyte, and we were able to get pretty decent results. With one cell, we were able to generate 0.5 volts and 0.2 milliamps. By connecting battery cells in series, the cathode of one cell to the anode of another one, you can effectively add their voltages together. So we treated each compartment as its own battery cell and hooked all 12 of them up in series. Doing this, we measured a voltage of 5.7 volts. The next thing that occurred to us is that maybe the higher the surface area of our metals that was in contact with the electrolyte, the more electrons could be transferred, leading to a higher current and higher power. To test this theory, we took one cell and measured the current produced when using 1 wire versus 2 wires and 3 wires of both the cathode and anode with the same dimensions. As you can see from the table, increasing the number of wires did improve the amount of current we measured. The final step for us was to figure out which electrolyte would give us the highest power. While we were conducting our tests with the number of wires, another group was testing different electrolytes and discovered that out of the options available to us, copper chloride yielded the highest current using a copper anode and aluminum cathode. With just one cell and one wire, they were able to produce a current of 0.19 milliamperes, nearly double what we got with potassium chloride. After choosing copper chloride as the electrolyte for our cells, we were now ready to assemble our battery and test. We connected all 12 cells in series, with each containing a wire of aluminum and a wire of copper, both coiled in 10 loops to try and fit as much surface area of metal and electrolyte in each cell as possible, while maintaining consistency from one cell to another. We dissolved our copper chloride salt and poured it into each of the 12 cells. Then we connected our 12-cell battery to our multimeter and circuit. I would say that the battery we produced was a success. Using it, we were able to simultaneously light 12 yellow LEDs. Our total current measured was 1.9 milliamps. Our total voltage measured was 4.8 volts, leading us to a power value of 9.12 milliwatts. Given the materials and time that was available to us, my whole team and I were proud of getting this much power out of our battery. This concludes my video on the basics of batteries. Hopefully this video has been helpful and interesting. If you enjoyed this video, like and subscribe.